Okay, so hi everyone, and welcome back to the second session of the meeting. My name is Andrew Daly from the University of Strathclyde in Glasgow, Scotland, and it's my pleasure to chair this second session and to welcome our first speaker for the session, Victor Galitski from Maryland. So Victor, looking forward to your talk. If people have got questions, please let's do the same as in the previous session, but please personal message me, and then I can either ask the questions for you or unmute you to ask the question of Victor, whichever way you prefer. Welcome, Victor. Looking forward to your presentation.
Well, thank you very much, Andrew, and thank you, David, for organizing this exciting meeting. Yeah, my name is Victor Galitski. I'm from Joint Quantum Institute in Maryland. So I'm a condensed matter / AMO theorist, and primarily interested in strongly correlated systems. So I have to apologize from the outset. I hadn't really realized that the focus of this symposium, of this conference, would be on analog simulations. So my talk is a little bit different. Maybe it's more relevant to the second day of the conference. But nevertheless, I'd like to try to make a connection. And let me do so by kind of fleshing out this cartoon, which is from a perspective we've been writing with Jacqueline Bloch, Andrea Cavalieri, Mohamed Hafezi, and Angel Rubio, who I understand is speaking tomorrow, where we basically have a landscape of physics that occurs at the intersection of basically, quantum optics, or in general, laser physics and condensed matter physics. So more generally, it's we're talking about electron-photon coupled systems. And the axes that we have here are interaction strength per photon, photon number, sort of quantum versus classical states, and electron correlations. And I am particularly interested, I'll be particularly interested in this segment, which will be this talk. And let me elaborate a little bit on that. So from the perspective of this, perhaps of this analog simulation standpoint. So we all know that cold atoms, of course, have been extremely successful in modeling various Hamiltonians and actually simulating interesting quantum dynamics and quantum Hamiltonians. But when we say interesting, we almost always imply actually interacting or strongly interacting. And if we want to achieve something like that, with cavities, with polariton physics, etc. So it may be a good idea actually to build in interactions from the outset. So far, for example, as we all know, polaritons and cavity physics mostly involved, semiconductors and such. But the key idea, kind of underlying idea behind the work we're doing, I'll be only be able to talk about a small slice of our work, is to take a strongly correlated material from the outset and couple it to light in such a way that the entities that are being hybridized actually already interacting. So, this is basically what this segment implies. And this also is motivated by recent work, which is seemingly unrelated, but in fact is very much related, on so-called enhancement of superconductivity in various materials. So I'll talk about it today. So today, mostly I will focus actually on superconductors, which are interacting materials that we actually understand. So, and the key kind of observational fact, which I'll elaborate more on, is that by irradiating, by external irradiation, one can induce or enhance various quantum coherent phases, such as superconductivity, for example. And one thing I'll be talking about is actually transient superconductivity above room temperature. And also, but this is done kind of in a transient way. So you have to shine light, you have to take an active role and kind of twist material into an interesting state. So what we're kind of trying to achieve is to bring this idea to cavity physics and to try to simulate or engineer, whatever you want to use the word. So interesting quantum phases, which are actually not transient, but they exist in some steady state. So, and this is what my talk will be about. Just remove this. So first I'll talk about kind of what's known about light-induced superconductivity in general. And in fact, this is an old topic which has been around since the 70s. And there is a very, very well understood phenomenon which is called the Eliasberg effect, And I'll talk about the cavity version of that. And then I'll talk about new developments in light-induced superconductivity and cavity-induced superconductivity, including recent experiments. And then in the second part of the talk, I'll talk about polaritons in interacting quantum matter. So again, the key idea is that instead of hybridizing, excitons with light, we can hybridize just about any collective mode in an interacting material with light. And in this particular case, I'll talk about so-called superconducting exciton polaritons, also called Bardassi-Schrieffer exciton polaritons, and Higgs polaritons. So anyway, so let me start with first part. So, and let me start gently with asking a silly sounding question. So what happens if you put a superconductor in a microwave, or just, if you shine microwave light on the surface of a regular superconductor, such as aluminum, for example. So, and the naive guess, of course, would be that, okay, we're just going to heat up and that's it. So it's going to be, superconductivity will be destroyed. So it turns out that this, in fact, is incorrect. And what happens is actually exactly the opposite. And so this was done first back in the 70s, in particular by Tuan Klepwijk. And what's plotted here is the critical current in a superconductor, which is a proxy of how strong superconductivity is. So the higher, the better. And this axis corresponds to the kind of power, microwave power with which you pump the system. So, and again, naively, you would expect that you will just kill superconductivity, but instead what happens is that critical current is increased, well, this implies actually enhanced superconductivity. And a similar phenomenon was observed with TC. So here, you see basically transition temperature. In the bottom line, I don't want to go into great detail. We can discuss it if there is interest. But essentially, there is some very interesting physics involving enhancement of TC, transition temperature in regular superconductors. Now, this was a bit of a mystery back then, but it was actually quickly understood by Gerasim Eliashberg. And this is known as Eliashberg mechanism. And I'll explain the essence of this mechanism because it will play a role also in related cavity physics. So essentially, what is a superconductor? You have a Bose condensate of Cooper pairs, right? So you condense Cooper pairs, and they're separated by a gap from single particle excitations. So this is the gap. And basically, to solve the regular superconducting problem means kind of in equilibrium means to find what this gap is as a function of temperature, for example. And usually, not usually, but what actually BCS theory tells us is that you have to solve a certain self-consistency equation, which involves essentially two parameters: interaction constant, the larger the better, and temperature in the Fermi-Dirac distribution, which is not negotiable. And that's it. And so if you know the interaction or temperature, out comes the delta. So what happens if you shine light on the superconductor, and if the frequency of the light happens to be smaller than the gap, which is actually the case for microwaves and aluminum, where if you translate basically a few Kelvin into frequency range, it will be about a microwave range. So anyway, so what happens is that you don't break up the existing Cooper pairs because you don't have enough energy. But what you do is that you evaporate existing quasi-particle excitations to higher energies. And what happens is that the distribution of quasi-particles is no longer a Fermi-Dirac. It's whatever, it's something else. And if you plug it in here in this self-consistency equation, so it turns out that this leads to actually a larger delta, which means larger, stronger superconductor. So delta essentially, again, is a kind of proxy of superconductivity. So this was the first example of both theory and experiment, which worked very well. It's a textbook thing, actually. So there is nothing exotic about it, which is very well understood, and it works. So, but the kind of downside of this, of course, was that you had to actually shine something, and it was a dynamic effect. And well, TC, enhancement of TC was, I don't know, from 1 Kelvin to 2 Kelvin or whatever. So it was sizable enhancement, but still low temperatures. So I want to mention actually as an aside that this Eliashberg's effect is actually generic in the sense that, if you don't like superconductivity, but excited about some other physics, for example, BECs, so it works kind of the same way. So it may work the same way. So essentially, say you have some equilibrium phase diagram and you have some interesting quantum phase at low temperatures that you care about and some classical liquid, or whatever it is you kind of don't care about, there's some quantum coherence that sets in at Tc naught. So, and this transition temperature is determined by coupling constants and the distribution of excitations. And in equilibrium, again, this distribution is non-negotiable. It's Fermi-Dirac or Bose-Einstein, but that's it. So, however, if you find a way to prepare a system in a generic steady state, either due to external radiation or coupling to cavity, for example, so essentially you add a whole new functional axis of all possible non-equilibrium states, and your quantum phase, your transition temperature, your order parameter become functionals of this distribution function. And so if you can engineer it in the right way, you can achieve perhaps a larger TC, not only in superconductors, but actually in other systems. So for instance, here in an old paper about 10 years old now, so in this paper, we discussed how to do it actually with cold atoms and to enhance superfluidity. So, but in general, it can be done in principle, for a variety of different quantum systems. Now, what I want to talk about is kind of taking this old idea, in a sense, and using it, marrying it with cavity physics. And this was done by my 3 students who all moved on. So Jonathan Curtis, who's moving to Harvard, Zach Rines, who's now at Yale, and Andrea Loca, who's in Cambridge, and my colleague in Maryland, Mohammed Hafezi. So in this paper last year. So essentially the idea is the general idea of what we want to do. And there's a cartoon, which I kind of borrowed from Jacopo's review and adapted it to my physics, is that we want to take a superconductor, maybe a microbridge or a film, something, something low dimensional, and couple it to cavity photons in such a way that as a result of this exercise, so the electrons will be redistributed in a more favorable distribution. So favorable again from the point of view of better, kind of stronger superconductivity. So, so this is one kind of genetic idea. And the second thing I'm going to be talking about is that, in superconductors and actually in a variety of correlated systems, so there are many, many different types of collective modes, excitations, and I'll talk about them. And just like exciton, which is of course just a kind of positronium atom in a weakly interacting, Coulomb interacting semiconductor. So in this strongly correlated or superconducting materials, you have collective modes that can be hybridized with light and can give rise to polaritons, much in the same way. So this is kind of the main idea. Now, let me go a little bit into the nitty-gritty sort of our theory. So again, what we want to do, so it doesn't, this is of course just a cartoon, it doesn't have to look like that, but we want to envision that there is some sort of cavity, generally, kind of generically defined. So where you have some quantum fluctuating, essentially a photon field, and you have a superconductor, which is kind of your active material that you want to improve. And so these are the 2 players in the theory, which are electrons in the superconductor and photons that interact with these electrons. And apart from that, there are also phonons, which are inevitable. Essentially, so there, in principle, there are different types of systems you can consider. You can consider photons and phonons having 2 different temperatures, or perhaps driven cavity. So there is a whole variety of different things you can consider, but this is kind of conceptually what you have. So you have this Bogoliubov quasiparticles in this 2-dimensional, let's say, superconductor. They exist in some bath, which determines the basis sort of temperature. And you want to enhance coherence above the equilibrium Tc. And again, the main idea here is that there is the good old BCS, Bardeen-Cooper-Schrieffer self-consistency equation, which determines how good your superconductor is. The larger the delta, the better. And now, the distribution function that features in this equation is something we want to engineer. And it can be engineered, well, theoretically, so it can be described by just solving a kinetic equation. So you have something which relates some collision integral that corresponds to photons interacting with electrons. And you have some relaxation mechanism due to phonons, because without driving or without coupling to cavity, they will just want to relax to Fermi-Dirac distribution at the basis temperature. And essentially, in order to find the distribution function in a steady state, you just set it to 0 and find the distribution function. So a little bit of the details of the theory. So, so how do you actually couple two photons in the superconductors? So it's done basically from first principles. So you just have electron current operator and cavity photon field, which are quantum operators. And so these are simply, I don't know, creation operator of electron, annihilation operator of electron, and some velocity field. So this is the current, and the quantized electromagnetic field. That's, you know, to write the Hamiltonian is very easy. However, in superconductor and in general in interacting systems, the quasiparticles are not physical electrons. So unlike, let's say, in semiconductors, where this is basically the coupling, so we have to remember so that the excitations in, let's say, superconductor are not that. I mean, there are some linear combinations of physical electrons, which are called Bogoliubov quasiparticles. And we know very well what they are. So the true excitations are what I call here gamma. It doesn't really matter what they are at this stage. And essentially, if you just expand this minimal substitution term, you will get all kinds of processes where photons can interact with this, basically can transform into Bogoliubov quasiparticles and vice versa. So, and there are actually four kinds of processes that, that exist. So, for example, we can have a process in which a high energy Bogoliubov excitation emits a photon and, you know, has a lower energy. We can have a scattering process in which kind of the reverse of it, where the electrons go kind of, the excitations go high up in energy. So unlike physical electrons, these quasiparticles are not conserved. So you can actually annihilate two quasiparticles and transform them into a photon. And this photon can just fly away basically because of the losses, which is a good thing. So this is a way of the cool system. And then there is the opposite effect, which of course is not good, which is due to pair breaking, where you heat it up. So and essentially, it's a combination of all these processes that will determine whether your system will have a better or weaker superconductivity. And again, just to put it in perspective, because I'm kind of focusing in a particular system, so all this can be generalized to other phases, right? It doesn't really have to be a superconductor. It can be some other system where you have quasiparticles. And so just the same way, you will have all these processes. So in any case, so the theory, unfortunately, is a little bit technical, and I'll try to just you know, very briefly go over this, just to emphasize one point, and this point will be disorder. So again, what we want to calculate is we basically have this kinetic equation which determines how photons and electrons interact with each other, and what we need to know is what is actually the collision integral. So this is something that can be done, and it's not easy, but it's straightforward in the sense it's essentially involves something like Fermi's golden rule. And there are kind of a few key ingredients: the distribution function of electrons, the distribution function of photons, and the kind of form factor, in some sense, which describes all these processes that I just showed in the previous slide. And this can be obtained from the Fermi's golden rule. And unfortunately, if you do so, you will find, for reasons that, okay, so I wrote some complicated equation. I don't expect you to understand what I'm writing here necessarily, but the point here is that we have a very weak coupling, actually. So it turns out that this coupling basically vanishes for low energy physics and also decays very quickly for high energy physics. And this kind of catch-22 situation can be boiled down to the momentum conservation laws. So if you do your theory in a clean system, you will have to kind of somehow take into account, you know, that electrons and photons have very different dispersions, right? There are very different energy scales involved. You know, speed of light is kind of large. So, and if you try to respect these conservation laws, you will have basically no effect. However, if you now include disorder, which actually you have to include because clean superconductors actually don't exist in nature, unfortunately, at least in 2 dimensions. So in this case, it's actually fortunately, so they do not actually exist. So all systems do have disorder. So these constraints are relaxed, and you get you can develop a proper theory, which I'm not going to describe, and relax these kinematic constraints and get actually sizable coupling. So with this, this I wanted to emphasize because I think this is actually an important point which we see all over again in trying to marry, you know, this cavity physics with interacting electronic materials, is that they just, if you do naive theory where you respect all conservation laws and don't include disorder, you may get an erroneous in my opinion, result where couplings are, some effects are weak, while in fact they're strong, if you recall that disorder does exist. So anyway, so once we have found this kinetic equation, to solve it is actually very easy. So all you have to do is just to set the derivative of the distribution function with time to 0, which means you're in a steady state. And this just becomes an algebraic equation for a distribution function. Well, if everything is in equilibrium, you get no effect, of course. If you just have a system and with some detailed balance, nothing is happening. But if you find a way to make photons, in a sense, different from phonons, so either by having them, letting them have different temperatures, or perhaps driving or squeezing, there are all kinds of things we can imagine, you do have an effect, and the effect is kind of strong. So here I will just show one example of our calculation. And what's shown here are change in the superconducting order parameter. Again, positive good, negative bad. So if it's up here, it means that we enhance superconductivity. If it's down here, it means that we suppress it, which is obviously not a very good thing. And the different curves here correspond to different temperatures in this case of the photon and phonon bath. So for instance, here, actually the photon bath is hotter than phonons, which is actually what happens in the Lashberg effect counterintuitively. But you can also have an effect where they're cooler. And this axis corresponds to the frequency of the cavity, basically, you know, in this cartoon, it would just correspond to the quantized, you know, standing waves. So in any case, this is our theory, and kind of the bottom line here is that these platforms, in general, platforms where you have cavity light interacting with interacting materials may be helpful in enhancing various interesting regimes. Now, I want to mention that you know, ours was not the only paper on that. So there were actually almost simultaneously there were 2 other papers by Dieter Jaksch and Andrea Cavalieri and Frank Schlavin in Oxford with similar ideas, and also Angel Rubio, who I think is speaking tomorrow. They also published a paper which is very much related. But this is theory. Okay, what's interesting is that there is actually an experiment. It's not quite the canonical cavity, but so this experiment still has the virtue of kind of actually existing. So what was done in Thomas Ebbeson's group is that so they put superconducting kind of grains next to a mirror, so the native TC of this superconductor is about 30 Kelvin. Actually, it's here, 30 Kelvin. But they have managed, not have managed, just, you know, did this experiment, and they found that their data on Meissner type signal is consistent with enhancement of superconductivity up to 45 Kelvin, which is a huge enhancement, of course. So, and this is very exciting, again, because, you know, this was, to my knowledge, the first kind of experiment that tried it, and it already saw an effect. Now, kind of just what I want to say here is that kind of the dream scenario and the kind of current frontier, if you want, is that we would like to, what I'd like to do is to combine these ideas that I just described, which were basically ideas for regular superconductors, with recent experiments by Andrea Cavalieri's group on light-induced ultra-high TC superconductivity. So let me just, you know, say 2 words about that and move on to Polaritons, actually. So basically the experiments, there are many papers now, but one of the first papers is this Nature paper a while back, 6 years ago. What they did, they actually were shining terahertz light, which was resonant with the phonons. So basically these are cuprates, YBCO, and these are layered materials. And what they were doing, essentially, they were shaking the planes. That's what they were doing. What they measured optical conductivity and found that they have basically signal consistent with TC superconductivity above actually room temperature, which of course has been extremely controversial, but extremely interesting at the same time. And what they also found is that this phenomenon was accompanied by suppression of so-called competing orders. So what happens in the cuprates are complicated materials, but essentially what you have there is superconductivity and some density wave instability, and they kind of fight each other. And what they found is that, well, for some reason, a density wave was suppressed, which they saw explicitly, and some proxies of superconductivity were enhanced. And of course, it was very exciting, except it's extremely short-lived state. Now, what we kind of want to do, and we have just the first paper on that, is that, okay, in the Cavalari's experiment, they tried something and it worked, but we don't really know why, actually. We don't understand these experiments. But what we do know is that one of the effects is the suppression of these competing orders. And one question we can ask is that, is it possible, A, to do it in a more targeted way? By it, I mean suppress these competing orders, and also instead of trying to achieve a transient state, get a permanent enhancement. So I see I'm running out of time, so maybe I'll just skip the details of this. But of course, I just wanted to see that the kind of dream scenario here is to replicate the experiments by Cavallari, but now in the cavity setup. And there were some ideas that we had, which according to Andrew, I have very little time. So let me actually just say that the main idea here is that if you have some, so there are basically two things you can do with light. You can enhance an effect, you can suppress it. So of course you want to enhance superconductivity, but if you happen to have some competing order nearby, you may want to kill it. So how do you kill it on purpose? So you kill it on purpose by exciting resonantly collective modes in the system by melting it. And so in the paper that I mentioned in the previous slide, so we showed how it may be done with van der Waals materials, which basically would be needed to match the dispersion relations. So now, in the last 5 minutes of my talk, I'd like to actually, say a few words about my original title, which is, more related perhaps to, tomorrow's day on Polaritons. And again, so this slide, of course, is unnecessary. We all know what Polaritons are. So they're hybridized states of excitons and photons in such cavity systems. And of course, one of the excitements is that these hybridized quasiparticles condense or appear to condense, or at least form coherent state, a laser-like state. You can argue whether it's spontaneous or induced, but whatever that is, interesting enough, even above room temperature. And the question we asked, is it possible to achieve something like that with an excitation in a superconductor? And in fact, there was a paper back in '61, theory paper by Bardasic and Schrieffer, which was literally called Excitons and Superconductors. So, so they were kind of predicted back in '61, but they actually observed just a few years ago, so in the Nick tides. Now, what are these excitons? It's kind of actually not such a simple concept. You may wonder why they're called excitons. And if you want more details, so this is the paper again with my students. So essentially, what these excitons are the following. So if you have a material in which you have a superconductor, so you have some coupling which actually pairs the electrons, right? So some attraction. So let's say, and there are many channels in which this pairing may happen. It's S-wave channel, D-wave channel, whatever channels. So, and the actual superconductor happens in one of the channels where the Cooper pairs form and condense. But there are also excited states of these Cooper pairs, for example, in the D channel, which don't actually realize that kind of empty states within the gap, but they do exist sort of as an isolated empty state. And much like excitons exist, excitonic states exist in the gap of a semiconductor, these fictitious, unless you excite them, D-wave pairs exist in the gap of a superconductor. And so this is what's called Bardasic-Schrieffer, well, it's not a very pretty acronym, but nevertheless, that's what it is. So Bardasic-Schrieffer modes or superconducting excitons. And so essentially they correspond to a fluctuating superconducting order. And for reasons I'm not going to explain, is that, if you condense into, let's say, this sector with this phase, so the Bardasic-Schrieffer mode fluctuates in the perpendicular kind of channel. So, I mean, the idea, I think you can probably guess what we want to do. We want to couple this superconducting excitons to light and produce what would be actually a very interesting topological like superconducting state and actually condense them to perhaps get a interesting polaritonic condensates. So again, in the interest of time, I'm not going to go into great detail. I will just say that these types of excitations actually don't couple to light very well. So in general, in superconductors and many other excitations we're looking at, they don't really couple to light naturally, but you can always make them couple to light. And one trick that has been actually used to observe them in experiment, not polaritons, but in a different context, is to run a current through the system, in which case they do couple to light. So yeah, if you want more details, you can ask questions or read the paper. But basically, the bottom line is that if you just take a native superconductor, don't do anything, and couple to light, nothing is actually going to couple to these fluctuating superconducting modes. But if you have supercurrent running through the system and disorder, which you do have, there's nothing you have to do about it. So you will actually see the coupling. And what you get is the usual picture, kind of, but now featuring a different type of polariton. So initially, you just have this kind of empty level of a fluctuating superconducting order parameter and light. And now you couple them to light, and you have the usual polaritonic picture. But now these polaritons correspond to S plus ID superconductor, which is interesting topological type superconductor. So yeah, so I'm now, I guess, completely out of time. I'll just mention that there was another idea that we recently published in this new journal of Physical Review Research. Again, along the same lines. Take material, kind of classify what collective modes you have, couple them to light, condense them, see what happens. So in this case, we looked at what happens with Higgs modes, and Higgs modes are, of course, fluctuations of the amplitude of the order parameter. And they have a mass. Again, the idea is that you want to couple these Higgs modes to light and obtain some sort of dressed Higgs mode state, which is a part Higgs, part photon. And yeah, we'll just say that it does happen. So although the theory is very interesting in that it doesn't have a Hamiltonian description, this is actually something I would like to understand better. Maybe some of you will have ideas. So usually when we write a polaritonic or excitonic, polaritonic Hamiltonian, you just write, A dagger B or whatever, some very simple Hamiltonian term. So here, Hamiltonian simply does not exist. So this theory is a kind of intrinsically dynamical theory in which you start with a Hamiltonian, you have to integrate out electrons and come up with some bosonic field, which you call Higgs, and photons. But this is no longer Hamiltonian theory. So in that sense, you can't really say how much matter, how much light your excitation is. So, but you still can observe, you can still plot an observable that you would measure if you actually do the experiment. And this has the interpretation of Higgs polariton. And that's very interesting. So yeah, and of course, an interesting question, what would condensing this Higgs polariton imply? So, so this is my summary. So basically what I've been talking about is that, first of all, superconductivity can be enhanced and kind of bootstrapped to high temperatures by coupling superconductors or granular superconductors to cavity photons. We still don't know what optimal protocols are for perhaps driving the cavity. So we also kind of explored a general idea of combining collective modes and interacting systems, including superconductors to light. And I talked about these superconducting polaritons and Higgs polaritons a little bit. Now, I just want to mention the last thing I'm going to mention is our recent, current, and future work. Again, under this umbrella of cavity physics and many body physics and strong correlations. So we're working on MOT polaritons, which are, again, strongly interacting polaritons in hybrid materials. We just recently wrote a paper with Ben and Jonathan on parallel instability by analogy between photons and phonons. And there are a whole range of other interesting ideas, which kind of, again, combine many body physics and cavity physics. So with this, I will just thank you very much and show my group. So these are the people who've been doing all the work. They unfortunately left now. Zach Ryans, Andrew Laka, and John Curtis. So thank you very much. Now stop sharing.
So thank you very much, Victor, for the nice talk. So sort of a virtual clap is always a little bit awkward in these online meetings. So we have a couple of questions already. The first is from Mark Ulrich. So I'll just unmute Mark and hopefully we can hear him.
All right.
Hi, Victor. Thank you very much for that exciting talk. I was just curious for one quick thing was these Bardacius-Schrieffer Polaritons, are they limited to have an energy below the superconducting gap, or is the non-equilibrium condition of these sorts of things allow you to go beyond that?
So, so actually the main challenge in observing these Bardacius-Schrieffer excitons, first forget even polaritons, was that oftentimes they were actually within the continuum. So for instance, if you have an isolated mode, but it exists in the continuum, it's basically going to decay immediately. So it's not going to work. So, but there are materials, in particular pnictides, where basically what are we talking about is that you have some interaction between electrons and you just kind of expand into Fourier harmonics, S, P, D, etc. And some of them are attractive, some of them are repulsive. And if they're attractive, they are kind of consistent with the formation of Cooper pairs. And it kind of depends what the actual energy is of these Cooper pairs. So if you're, so basically you have, Cooper pairs, you have excited states, and you want this isolated mode to be within the gap. So, in the pnictides, it's already the case that they are within the gap. So what's actually interesting in the case, in particular in the case of actually Higgs modes, is that you may start with a material in which this isolated mode is within the continuum, which again means just decay, just forget about it. And by coupling it to light, you kind of lower it into the gap and make it stable. This, in fact, is the whole idea of our Higgs paper, because Higgs mode and the superconductors have been really difficult to measure. And part of the reason is that, again, it kind of, it coexists with a bunch of excitations. And even if you excite it, just decays too fast. But if you couple it to light, you create two modes. One goes within the gap, the other is forget it, but the one within the gap is very stable. It's immune to dissipation. So essentially, it's a question of energetics of particular material. So there is no universal answer. So, but in principle, I don't know if that's what you were asking, but you may start with the material in which you have an unstable mode, couple it to light, it becomes stable as a polariton.
Great. Yep. Very helpful. Thank you.
Okay, so the second question is from Vincent Liu. Vincent, I'll just unmute you and hopefully.
Let's see.
Oh, really enjoyed the talk, Victor. So I have a question regarding this S plus ID superconductor based on the interaction induced by the polariton, right? Coupled to the Cooper pairs. This is related to Mark's question a little bit. Mm-hmm. So it's quite intriguing. So it's S plus ID. Then I was thinking the photons carry angular momentum h bar, 1 h bar, right? Mm-hmm. So I was wondering why you don't get S plus IP instead of SID, S plus ID. Is that because the Cooper pair carry charge 2e, or is that simple?
No, it's not so much about the charge. Actually, these modes are all neutral, by the way. So these are neutral modes. So so the order parameter itself, the fluctuations of the order parameter are actually neutral modes. So, but you have some selection rules. And in fact, it was, I think, discussed in the original paper by Bardacius and Schrieffer that, so you kind of want the same parity. But in principle, there is nothing preventing you from, so first of all, if you have a real material, you have to classify your Cooper pairs according to the symmetry group of your material. S, P, D, etc. is just, it assumes that you conserve angular momentum, which in the presence of a lattice, you actually don't. In principle, you may have, if you, for instance, if you're interested in the P wave-like physics, in principle, you may get it. There's no obstruction to it if you break some symmetries. But in a kind of naive model, if you want, of, basically what Bardacius and Schrieffer have actually considered, you can't have mixing parities.
So now in a continuum, the message is that in a continuum without lattice, the selection rule will prevent the P wave component from happening.
So unless you break by symmetry, some symmetries by hand, because you have even and both mixing up, and it's usually not very good. Unless you break a symmetry, it's just not allowed essentially. So, but S and D are okay, or S and any or even parity. But again, if you start with it's not a problem really to break a symmetry. In principle, there is no problem with that at all. So I mean, if there is a reason to achieve something like even maybe P plus IP or S plus IP, or with an existing ground state, which is friendly enough, so you can do that. I'm pretty sure one can cook up something.
So just a follow-up, is this related to the way you use the light to implement angular momentum to the superconductor? So can view this like a vortex, the excitation as a way like a vortex?
No, it's not so much that actually. It's just, so again, the picture I have is that, okay, so say we take semiconductor, valence band, conduction band, and there is some isolated state within the gap. And you want an operator that converts a photon into this state, right? So this is what, kills a photon, creates an exciton, and vice versa. Well, let me look at this picture from a generic point of view. It doesn't have to be a semiconductor. It can be, I don't know, Mott insulator or a superconductor, whatever you like, okay? So you have, as long as you have a gapped state and some isolated state within the gap, if you manage convert a photon into this state, you're done in the exact same physics, essentially. I mean, well, there will be complications, but these are good complications. It's actually strongly correlated complications for me. So in this case, you have a superconductor where you have basically kind of condensate and some Bogoliubov excitations up there. And within the gap, this is the Bardassi-Schiffer's result, you do have actually an isolated state, which is this fluctuating D-wave pair. And your goal is basically to kind of resonantly couple to it, much like you would couple to exciton. You see? So, and well, again, it's been observed in materials, I can say, in some Nature, whatever paper, just a few years ago. It's actually a very recent development. So, so it's a reality, but Polaritons have not been observed this way. So it's just a theory for now. So I don't really know the status of experiment.
Okay, so we have one more question before we move on to the next speaker. The final question is from Amitava Banerjee. So I'll unmute you and hopefully you should be able to.
Hi, yeah. So this is Amitava from Maryland. Thanks, Victor, for the great talk. So my question was, what are the prospects of doing analog computations with strongly correlated systems? So for example, can one use the response functions of these materials to infer anything about the cavity light field? Like Sanjeev Ghosh's talk, we see that he can infer about entanglement properties of the input field. Or can you do the opposite, like getting quantum correlations in these materials from measurements in the light field?
So yeah, I'm actually have to admit, I'm not exactly sure where there is a line between simply measuring something and computing something, because so far, I don't know what that means actually, analog simulation. So what I find interesting in the context of cavity physics, so I mean, I don't know, I don't think with anything everything I've been talking about just basic physics. I didn't have in mind any simulation, but again, so the connection I want to make is that, say, we're excited about cold atoms. Why are we excited about cold atoms? Because interactions are tunable, right? So you have tunable interactions in principle, and you can cook up different Hamiltonians. So what I'm saying is that, why don't we take a strongly correlated material from the outset, couple it to light, and play with it, where you already have interactions built in. So instead of trying to, build them up using the light. So there are actually two routes. You can take light and make it mediate interactions, or you can take material which is already strongly interacting, couple it to light, and both are actually interesting. So, and I think in the latter scenario, which interests me, so, you could have a situation which is quite similar to cold atoms, where you could have some resonant interactions, light, tuned by light, et cetera, et cetera. So this is perhaps the route which is most relevant to your question, but I don't have a particular algorithm or whatever for analog simulation. I have no idea, sorry.
Great, so thank you very much again, Victor, for the nice talk and for the nice answers to the questions. So I'll clap on behalf of everyone again.
Thank you very much.
And